for a number of years, I've been in this stuff that I and others also call epistemic planning. So the idea is that there's a long tradition in AI for doing automated planning. And the idea in automated planning is that we are given some initial. Wait a second. Yeah, now this is a bit different. Because I don't go full screen. So give me a second here. Yeah, okay. We're given some kind of initial state of a system, or like it could be a robot, whatever, and some kind of goal, and then we want to find a sequence of actions bringing us to the goal. And I mean, places where it's used is, for instance, in robotics, like the robots in the Amazon warehouses. So that's been something people in AI have been looking a lot at. And it's somehow, from a logician's perspective, it's a nice, clean area where somehow we have well-defined, well-known algorithms. We can study their complexity, their properties, and we can even use logic. And people actually, even in this area, do use logic to describe states and describe actions. Now, what they typically don't do is to look at epistemic aspects of this. So classically in AI, they've actually only even looked at one agent acting and planning and ignoring all other agents. And of course, that creates a lot of limitations. And it's very interesting to look at let's say, the generalized multi-agent case, where you can take the perspective of other agents, you can take their mental states into account. So you have some kind of theory of mind where you can reason about the goals of the other agents, you can reason about their abilities, you can reason about their beliefs, about their knowledge, etc. And again, from a logical perspective, that brings us then into something like for instance, considering epistemic logic, or at least considering something with Kripke models, because then there is some uncertainty and we have to somehow represent this uncertainty somehow, right? And a Kripke model is a very natural place to do these kind of things, because we can have multiple modalities, one for each agent, and we can have different types of modalities depending on what the uncertainty is. And Kripke models is all about uncertainty. And of course, there will be uncertainty, because even if we try to get into the heads of other agents, whether it's humans or robots or whatever, we don't know exactly what is going on. So we need to be able to represent the uncertainty, and maybe also higher order uncertainty. So that's just the starting point. And when it's completely classical, then as I said, we often have these logical representations. So also people in AI have that. And it could be something like this. So this is classical the blocks world problem. So if you look at the camera stream, right, you can see you can see me, right? Also, yeah, good. So we have these three blocks, and C is on top of B, and B is on top of A. So that corresponds to my initial state here. What I want to achieve is that the blocks are stacked in the opposite order. And the idea is then that, well, we describe states as logical description. So it can be a conjunction of atoms of first order predicate logic. And then we have actions, and these actions are transforming the logical description of the state. For instance, if I take block C down, I'm in another state that can be described like this. Okay. Now, in classical planning, they have these so-called action schemas, and these action schemas, well, they have a name. So I have an action for putting X on top of Y. That has some preconditions in terms of where, like, X is currently located on top of Z, say, and it has some effects. Like if I take X and put it on top of Y, well, then the effect is that X is on top of Y and it's no longer on top of Z. So, and if you know, and I guess many of you know about dynamic epistemic logic, but even if you don't, right? So there are these extensions of epistemic logic where we have so-called event models for describing the dynamics. So the idea is that we have some language also to describe the dynamics of how things change, and that also is something that people do in um, in automated planning, so classical automated planning in AI, and it's also something that people then do in dynamic epistemic logic. So we can try to generalize from what people do in classical planning to something that builds on top of dynamic epistemic logic. And this is what then I've spent, well, it's been one of the main things I've been doing for actually more than 10 years. I've also been working on other things, but I've spent a lot of resources on this, and trying to look into this. And then you might say, okay, why? Okay, what? So one thing is you need to stack blocks in a particular order, or you're an Amazon robot and you need to move shelves from location A to location B. And then what is all the fuss about the multi-agent stuff and reasoning about that? So let's try to look at one example of where that becomes interesting from the realm of real human agents interacting in in real scenarios. Well, okay, is it a real scenario? It's a psychological. Well, it's a test in cognitive psychology, and so the scenario is of course uh, not necessarily supernatural, but I'm pretty certain the behavior of the child here, who is the test person, is natural. So let's see what happens. Let me know if the sound doesn't go through, because I clicked the one for choosing the sound, but you never know.
Oh. Hmm. Oh. Hmm. So.
So that's the kind of kids we all want, right? That are helpful, and only, not even are they helpful, they don't even have to be asked to help. They just help, right? So Warneken and Tomasello, who made this, like they study altruism, but they, I mean, but they also study a lot theory of mind, and also in animals. And of course, there's some discussion going on about what we are seeing here and what kind of cognitive processes are taking place in the child. But if we wanted to model something along these lines from an AI perspective, right? What the natural way, I think, is to think about it is that, first of all, that somehow the kid is not active unless he knows what the goal is. I mean, there has to be a goal somehow, but the goal is not explicitly stated. How does the kid know the goal? Well, he sees the adult bumping into the cabinet with a stack of papers, and he realizes that that is the goal, and somehow that the adult cannot, or doesn't know how to, or because he has his handfuls, he cannot get into the cabinet, right? But that is really theory of mind. It's the kid reasoning about what goes on inside the head of the adult, and trying to represent the mental state of the adult. So what kind of goals does he have? What kind of actions does he have available? What is his planning capabilities, for instance, right? Why doesn't he just put the papers on the floor and open the cabinet doors and put in the papers? So and of course, I also mentioned in my abstract that I wanted to talk about implicit coordination, and there I'm also inspired by scenarios like this, because of when we talk about multi-agent systems in AI, uh, often, like what they do at Amazon, for instance, with these warehouse robots, is that they solve problems in a centralized manner, so it's not really a multi-agent system anyway. And when we have real multi-agent systems, then even if we have a joint goal, and even if we allow the agents to plan for themselves, we probably have some kind of protocol or architecture that decides how the agents agree on the plan, that they kind of negotiate about what the plan should be, or what actions they should be, or they negotiate about the possible conflicts. At least that is kind of fairly standard in multi-agent systems. But here it's really not about that, right? There's no there's no at least explicit coordination or communication, right? It's just that the child observes that there's some help needed, and then he helps, and then it's done. Okay, so just keep that in mind, because later I'm going to give you some examples of how I then model this implicit coordination stuff. All right. Now, right. So I said before that when I wanted to solve this problem with my blocks, and I'm a single agent, and I'm looking at the letters of the blocks, well, I just represent the state as saying which blocks are stacked on top of which other blocks, and I'm kind of done. There's nothing to it. But let's assume that maybe we have a situation where there's non-uniformly distributed information about these blocks. So what could that be? It could be that, for instance, okay, so now now I'm looking at the letter of the block, and you're looking at the letter on the middle one, and the problem is still the same, and we somehow to solve it together, right? Of course, if we need to solve this problem together, I, it doesn't make a lot of sense if I cannot represent your mental state, because if I cannot, then I have no idea about whether what you are seeing and what you know, and I don't even know which questions to ask, for instance, right? And vice versa. If you cannot reason about my mental state, you don't know what information is relevant to me. So somehow it seems well motivated to say that these agents want to represent the mental states of each other, and we can do that with S5 Kripke models. And again, you probably know these, but just so let me do it very briefly, right? So if we model things from the perspective of the blue agent, then we can say, well, the blue agent thinks that the stacking order is either CBA or CAB. Why? Well, because the blue agent only sees the letter on the top block. Now, but the blue agent knows more than that, right? Because if the actual stacking order is CBA, then the blue agent knows that the gray agent is looking at a B. And what does that mean? Well, it means that the gray agent thinks that either the stacking order is CBA or it's ABC. So we can have an indistinguishability edge here for the gray agent, saying that, okay, if the middle bug is indeed B, then the gray agent considers it possible that either the stacking order is CBA or it's ABC. Right, and we can continue this picture, and then we get a nice S5 Kripke model like this, where the edges represent indistinguishability for the two agents. And why is that nice? Well, it's nice because I can use this for planning, because then I can say, oh, for instance, the blue agent could consider asking a question to the gray agent. For instance, the question could be, which letter does the middle block have, right? That's an action. Okay, it's a speech act, but it's an action that one can perform, and that action should have some effect on the state. And now, because the states are epistemic, indeed, it does have an effect. It has the effect that the answer you will get the answer, and the answer will cut all these links. So let's see, why would we cut these links by asking that question? Well, it's because all these links represent the states that the blue agent cannot distinguish between, right? And of course, if the blue agent asks about the letter on the middle block and the gray agent answers truthfully, etc., then the blue agent will have no uncertainty left, right? Because then the blue agent will know exactly how things are stacked up. So it's quite nice to actually use these models to in a planning setting, because then also questions and information, I mean, announcements, all that kind of stuff that seems very natural to have when multiple agents are collaborating, that you get somehow you automatically get a formalism that can handle that. Also note, I have these designated worlds, and I'm using multiple designated worlds or multi-pointed models, and that's because there can still be some non-determinism and uncertainty for the planning agent. So even if we're looking at things from the blue agent's perspective, but the blue agent might not have full the blue agent obviously doesn't have full information. So it might also be necessary to have multiple designated worlds to account for that. And in this particular case, what we can see here is that when 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 the blue agent is deliberating about asking this question about the middle block and reasoning about the consequence of it, the blue agent says, oh, afterwards the model will look like this. And since there are now these two designated worlds and they are not connected by an indistinguishability edge for B, what it means is that the blue agent knows that either the result will be that we are in this state or that state, right? So either the result will be to know that CBA is the correct stacking order or that it's CAB. But also, the blue agent knows that the gray agent still doesn't know the correct stacking order. So also from this model, we have the information that even if the blue agent now restacks the block in the correct order, then the gray agent still doesn't know it. So if the goal is that this is common knowledge, then you still have to make an announcement at the end. So there's a lot of information we can get out of these models. Now, dynamic epistemic logic. So again, probably many of you know it, and I will just very, very briefly illustrate it with a very simple example. So this is an example where we have free agents A1, A2, and A3. Okay, and the idea in dynamic epistemic logic is to extend epistemic logic with, well, dynamics. And what does dynamics mean? Well, it means that um, um, that we can represent actions, and that we can represent the result of executing actions in states. But the states are now Kripke models. So we have possible worlds, we have indistinguishability for the different agents. And the actions are actually similar. They also build on Kripke frames. We also have nodes and edges for agents, but these nodes are now events. They are representing things that can happen in the world. So in this particular case, we have a door that is either unlocked or locked. So that's the initial situation. And A1 and A2 don't know whether it's locked or unlocked. Okay, so that's where we start. Then we have an action of opening the door, but if the door is locked, nothing happens. So that part is represented by the event over here. So you can think of it as like saying that now there's some non-determinism going on, and also there can be uncertainty about when something happens, what is it that actually happens, and different agents have different views on this. So this event over here is representing failure. It's representing the situation that when the door is locked, nothing happens. Right? Okay, you try to open the door, it doesn't work, it's locked. Okay, if it's unlocked, then it will be open. Okay, and then the way we compute the result of attempting to open the door, well, actually, it's also A1 doing it here. So A1 is trying to open the door in the initial state. And the way in dynamic epistemic logic it works is that we take one event at a time. So this is one of the things that is a possible event, a possible thing that happens. Then we look at which worlds it applies to. It says the precondition is unlocked, so it applies to the unlocked world. What is the consequence? Well, the consequence is that open will become true. Okay, so it produces a new world in which open is true. Okay, but there's also another event, the failure event. It requires that the door is locked. Okay, where is it locked? Well, it's locked in this world. Okay, so out of that pair consisting of a world of an event, we construct a new world. And since there's no post condition here, we just preserve the valuation of that world. And then we add up the edges at the end. And let's look at the edges, because that's a bit interesting here. Because what we are saying now is that initially A1 and A2, they don't know whether the door is locked or not. And when A1 is opening or trying to open the door, A2 and A3 are not looking. They're not seeing it. So who is it eventually that still doesn't know whether the door is open or not? Well, that's only A2, right? Because it's unlocked. So A3 will know that it's unlocked and now open. A1 will one doing it, and then one is seeing what she's doing, right? It's only A2 who still has an indistinguishability edge here because it's inherited by the indistinguishability edge up here and the one down here. Okay, so so that's very quickly how this del product update works. And the idea is that, well, we can describe any type of complicated action as a del event model, and then we can apply it, and then we can start looking at what it means to plan over these structures. But before planning, right? So because we can also say, well, one thing is you can plan. So I mean, you have a goal. We want to see how to stitch together our actions to achieve the goal. But we could also just look at belief tracking or knowledge tracking. So we have a situation where something happens, we see people or whatever to understand who knows what about the state. And some of the stuff we did on human-robot collaboration and interaction is just doing that. So it's not about planning. It's simply about like belief tracking. And here's a very, very simple example. So let's say that we have a cube, and this cube is either in box 1 or box 2. And there's a human, so this is the human, and there's a robot. So R is the robot. Now, initially, let's say that the cube is hiding in one of these boxes. Let's say there's only 2, despite there being 4 in the picture, but let's say there's only 2. And the cube is hiding in one of these, and neither the robot nor the human knows. So then we have a situation like this. Let's say now that the robot peeks inside one of these boxes. So it peeks inside box 1 and checks what is there. Now, the robot can represent that as one of these event models where there's an age indistinguishability edge here. So what does this express? It expresses that, well, either somehow we get the robot gets the information that the cube is in box 1, or the information that it's not. Right? You peek, you look, you see whether it's there, but the human doesn't see it. Right? So here we correctly represent the fact that if we look inside something alone, or we open the fridge and check what is inside, right? Other people behind us might not see what we see, right? They see it that we see something, but they don't see what we see. So when we construct a product update, we get a situation like this, where we actually have exactly the same model as initially, except now the R relation has been removed, right? So and the point about this, so we have been using it for scenarios where we wanted the robot to be helpful in searching for things, right? So we can could be a situation where, I don't know, I lost my glasses or something, and I'm trying to find them, and there's a robot trying to help me find them, right? And of course the point here would be that if the robot finds them inside a cabinet or something, it should inform me, right? But how does it know that it should inform me? Is that kind of hard-coded in the system? Well, it could be, but that's not an elegant solution. And an elegant solution would be that the robot knows that it has to inform me, because the fact that the robot knows doesn't imply that I know, right? So and this is exactly what we get by modeling it with dynamic epistemic logic, that we can keep track of representing the mental state of the other agents. So, and if we look at something very simple, also again with real human agents, if we look at something very simple with this theory of mind stuff, where it's about belief tracking, then there's this famous Sally-Ann test, and so it's one of a fairly large class of so-called false belief tests or false belief tasks. I'm going to show the video, and then I'm going to next show you how we make our robot pass it using the dynamic epistemic logic updates, and then I'm going to talk a bit about how we did it. So let's go.
And this is Anne. Oh. Okay, this is Sally, and this is Anne. Which one's Sally?
This one.
Well done, right. And Sally has got a basket. And Anne has got a box, nothing in it. And Sally has got a marble. And Sally puts her marble into her basket to keep it safe while she goes outside to play. But while Sally's outside, naughty Anne moves the marble from Sally's basket into her box. Naughty Anne. So where's the marble now?
Box.
Good. Where did Sally put the marble in the beginning?
Basket.
In the basket. Well done. So when Sally comes back from playtime, where will she look for her marble?
In the box.
In the box.
So did the kid pass the test? No. No. So the thing is, Sally was outside, right? And she didn't see that the marble was being moved. So then, of course, we can start talking about intention recognition and she's naughty and all that, right? But the standard interpretation here is that we have some kind of epistemic inertia going on, that where you don't expect things to change yet, where you haven't seen them change and you haven't like any reason to believe that they were changed. So, but the thing is, in order to pass the test, you need to be able to represent the mental state of Anne and of Sally and what goes on in the scenario. And this is what we then used dynamic epistemic logic for. So let's have a look at that. So we used one of these robots. It's a so-called Pepper robot from SoftBank Robotics. We adopted, since I'm from DTU, we adopted R2 DTU. And here we have a version of the Salian test. We have objects and containers, and we are trying to make it more general, so you can have any number of objects and containers, and we can move them around as we want to, and people can move in and out of the room as they want to. But now we are putting objects into these containers, and the robot is looking at both Lasse, my former student, and I, so it sees that we both know where these objects are, right? But of course, that might change if Lasse leaves the room. So if I ask him to go outside, and if while he's outside, I make some change to the state. So what I'm doing here is I take the red cube and put it into box 2. And now the robot knows that Lasse didn't see that. How does it do it? Well, there's a lot of deep neural networks under the hood of the robot. So it's doing face recognition, it's doing skeleton tracking, and it's tracking these objects with the QR code. So there's a lot of machine learning going on as well. But we take the machine learning part in order to create percepts that we translate into logic, right? So the logic part is like when the robot has perceived things in the world, and what it will perceive in this case, for instance, is that it can no longer see Lasse, right? He's gone. So it will assume that he has gone, and whatever happens afterwards is, of course, something that he doesn't see. Okay, so now I can ask the robot. R2-DTU, where is the red cube?
The red cube is in box 2.
R2-DTU, where does Lasse believe the red cube to be?
Lasse believes that the red cube is in box 1.
Okay, so it passes the Salian test, and of course we could also have hard-coded it, the answers, right? But that's not what we do. And also, we're not even the first to make a robot that passes the Salian test. That happened back with Cynthia Brazil at MIT many years ago, right? But the difference is that she was kind of hard-coding a first-order theory of mind, saying that, okay, so we have this robot, and that has a mental state. And it also creates a mental state of other agents, which is a copy of the same kind of module. So there was no logic or no principled approach. There was no, it was not possible to prove theorems or prove properties. So I mean, here we can actually show that because we're using a very strong and well-defined logical approach, we can show that, I mean, as long as the robot doesn't do any perception mistakes, it can actually keep track of it. I mean, it can correctly keep track of these mental states of other agents, also the higher order ones. We also experimented with crazy higher order false belief tasks where we even ourselves lost track, but the robot were able to still do it. It's actually quite interesting that if you go to some of these higher order false belief tasks, then some of them are only robustly answered correctly by human beings around the age of 23 or something, right? So this is something that actually keeps developing in the human mind for many years. Also, like when we are starting to get adults. Anyway, so back to the logic part of this, right? So again, this is a Kripke model. What is special about it is that we have these seeing propositions. So this says A sees B and B sees A. So we are A and B, less than I, my ex-student and I. But this is not. We are extending a bit the formalism to have this notion of who sees who. And over here we have a dynamic change of who sees who. So here we made an opposite experiment where I'm the one leaving the room, but it means that we stop seeing each other. So what goes on here is that this is the kind of internal representation of what goes on when the robot sees something, right? It makes perceptions, it translates these perceptions into event models in Dell, it applies them via the product update, and then it keeps keeping track of these mental states. And here in the final mental state, we have that B. So that is Lasse. He only considers it possible that the red cube is in box 2, so he moved it to box 2. Whereas A, me, I only consider it possible that it's still in box 1, right? So that's it. And then let's take a move from there to no, let me actually do this first, because I've been talking a bit about like the structure and the neural networks and stuff. So let me take this slide and then I'll move back. So this is like a classical view from AI. What the view of what an agent is something that is situated in an environment and it receives percepts from the environment, and those are processed somehow and turned into actions in the environment, and then we have this kind of loop going on, right? And the way we process the sensor input is that we split into a perception layer that uses deep neural networks, and then we have a cognition layer that uses dynamic epistemic logic and planning techniques on top of that, right? So let's go back and look at planning on top of it, right? Now, in classical planning, as I said, we can use classical logic, like first order predicate logic, or like even a subset of that. And when we go to epistemic planning, then we represent states as Kripke models, and we represent actions as event models. We represent goals as formulas of epistemic logic. And in the simple case, a solution to such a problem is just a sequence of actions that takes you from the initial state to the goal state. We also look at policies and stuff, but in the simplest case, it's just a sequence of actions. So a solution given an initial state, some actions, and a goal formula phi g is a sequence of actions, alpha 1 to alpha n, so that if I take the product update, so this means I now execute these actions one after the other in the initial state, and I check whether the goal formula holds at the end, right? And that's it. Now, I also have applicability up here, right? Because I need to check that my actions are applicable. Because before I had an open door action that said, okay, it explains what happens if the door is locked and if it's unlocked. I might also have an action for opening the door that assumes the door to be unlocked, right? So there's no event describing what happens if the door is locked. Okay, that action would not be applicable from the perspective of an agent who doesn't know whether the door is locked or unlocked, right? So an applicability is well-studied notion in classical planning, but okay, so we also need to introduce that here. And in a dynamic epistemic logic setting, we can express applicability via diamond. So this thing essentially says that the action alpha is applicable because there's a possible execution of alpha that leads to top. And then I can express that alpha 1 to alpha n is a plan, a solution like this with this new modality. Now, I promised also, I mean, to talk about implicit coordination, and the question is, what is it? And when we talk about policies and stuff, it gets a bit tricky. But when we only look at sequential plans, it's not that bad. So the idea in implicit coordination is you have all agents have a joint goal. They all want the same, right? So again, it could be something like this. Maybe we are together trying to solve this problem with the blocks. And maybe we take turns, for instance, to move a block, right? But we all want the same. We all want to stack these in alphabetic order. Okay. So so what does that mean? Okay, so now let's look at the case where I don't see the letter of any of these blocks, but you see all of them. Now I'm the one in the room with the blocks. I can move them, right? But you cannot. But you can inform me about stuff, right? So in this situation, like how would we solve this problem together? Of course, like intuitively, if I cannot turn them around and have a look, you would have to give me some information, and I can use that information in order to stack them in the right order, right? Now we need to somehow see how formally to deal with that, and then the idea is that a plan is implicitly coordinated if the agents know. So as you can, let's go back to the slide for a second and look at the formulation here, right? So now we look at actions as being executed by agents. So alpha 1 is executed by I1, etc., up to alpha n is executed by IN. So this is implicitly coordinated if I1. So the one who performs the first action knows that by performing this action, the agent who is supposed to perform the second action knows that by performing that action, we get to a situation, etc., until we get to the goal. So why does it make a difference here? Well, it makes a difference because if you are trying to plan for the restacking of these blocks, but you know that I'm also part of the system, I can also do stuff, right? But if you just plan from your own perspective, you just say, oh, it's clear. I mean, Thomas has to take this one down, and then this one, and then this one, and then he will be done, and you won't even tell me, right? because you cannot move the blocks, so you just rely on me moving the blocks. But that doesn't work, obviously, right? Because I don't have that information. So you have to reason otherwise. I mean, you have to also include some of your own actions in here, and these actions are giving information, right? And then you can say, oh, you can, for instance, inform me that the top block is C. And then you know that by informing me about this, I know that I can take this one down. And then you know, for instance, that you can inform me that the next one is B. And then I know that I can put B on top of here. And then I know which one is the last one. And then we're done, right? And the latest thing we are working on here is forward induction in this setting, and have to be a bit careful with time, I guess. Yeah, so no, but let me just very briefly talk about that. I don't want to go into detail because we are writing a paper about this now, and it took a lot of time to get that correct. Yeah, and sensible. And if you know something about epistemic game theory, then well, you probably also know that these things are not very easy. Anyway, so the thing is, let's again say we need to restack these in alphabetic order with A on top and C at the bottom. And let's say now you are seeing the letters, I'm seeing nothing. Okay, and it's on top of that, it's turn-based, right? So we take turns to perform actions. Okay. So let's say you first take this one down. Okay. And then I take this one over here. I don't know what it is, but I'm just doing it, right? And then you do, now I have to be a bit careful. Then you do this. Okay. So what do I do now? Well, I should know. I know not. I mean, I know not. In principle, I know nothing, right? Because I have not received any information. But I should know that since you put this block on top of that one, this must be a B and this must be a C and then this must be an A. But how do I know? You didn't tell me. I only knew because of this action being optimal for achieving the goal, right? So I'm reasoning now about somehow the rationality of your actions. So I reason and say, okay, but supposing that you are rational, I can exclude the possibility that the stacking or that the letters are different than exactly this, and then I know I can do this and we're done, right? No communication at all. We just solve the problem. So okay. So this is the kind of stuff that I got interested in lately, with this more like in towards forward induction and like taking this implicit coordination stuff even a bit further. Also because we see a lot of this kind of implicit coordination in real life. Also referring back to the case with the adult and the child, right? There's a lot of stuff going on between humans and also even with animals where it's not negotiation, it's not a fixed protocol, at least it doesn't seem to be, right? It's really about interpreting the actions of others and having expectations of their actions by reasoning about their mental states. So here's an example of applying that. Lazif, welcome back. Oops.
Hi.
Sorry. Hello, Lazif, welcome back.
Hi.
So what are you up to?
So I have come to fetch the blue cube.
Ah, okay.
Also, I need the red cube.
If you are looking for the red cube, it is now in box 2.
So here the point is that the robot is reasoning about the fact that he has a false belief. He's reaching out. It's not listening at this point. It just sees that he's reaching out for that box. And then it sees that he has a false belief about that box, and then say, oh, if you're reaching out for box 1, you clearly want to interact with something you believe it to be in box 1. And that is the red cube, right? So and of course in human robot interaction and collaboration scenarios, these are important things, right? Because if a robot sees a human going to the fridge and opening the fridge to take something out, and let's say that you're out of milk, so there's no milk in the fridge, right? If the robot doesn't have a theory of mind of the human, it would never be able to believe that the goal is to find milk, because there is no milk, right? I mean, it only works if you can actually represent mental state of and also when mental states are incorrectly representing the true state of affairs. So I'm also working with a roboticist from Örebro University. I'm going there next week to look at like proactive behavior in robots based on these kinds of models. Okay, so let's see. So I think if I look at when I started, that's approximately 15 minutes left, but I still have a few slides with some
yes, don't
complexity.
worry. I mean, you have time. You
Okay,
still have time.
yeah.
You can go on. I would say 10 minutes, and then there is the question and answer session. But we're not too strict on this, so take the time you need.
Okay. Yeah, good. Thanks. Yeah, don't say that to me though. It will be 5 hours. But anyway, I mean, and of course you can also, when this is not fun anymore, you just leave, right? That's how it is. Right. Okay. So I mean, I spend quite a lot of time on motivating this kind of stuff because I think it's important, right? And I think and I think it's nice also to see that somehow logic can be useful in these settings, and actually it's necessary, right? Because I looked at all this stuff from AI and robotics, and where they talk. I mean, people are getting more and more aware that theory of mind representation is crucial, but there are not many people who have a strong, let's say, techniques and theoretical frameworks to actually work with it in a principled way as we have in logic, right? So I think it's really nice that also logic can contribute in this way to something that is at least closer to mainstream AI than a lot of other things we do in logic. But anyway, I mean, so the thing is that you might also say, now I define what a solution is, and then as you saw when we start talking about implicit coordination, things get a bit more tricky, because then it's not completely clear what it means, and then we get into something that relates to epistemic game theory, and then it's okay, so that's one of the places where things get a bit complicated. Another place is like with complexity, because in classical planning, we are in finite state spaces. There's only a finite number of possible combinations of things, right? You have finitely many constant symbols and finitely many predicates, and they can only be combined in finitely many ways. Now, of course, we know that in epistemic logic, it's not true we can only build a finite number of Kirke models, even if we have a finite alphabet and a finite number of agents. So potentially this might be bad news for trying to plan over these structures, because we're not guaranteed that planning is even decidable. So first of all, what does decidability of planning mean? Well, the classic decision problem is the plan existence problem. So that means we have a planning task, we have an initial state, some actions and a goal. And then we ask, is there a solution? Can we solve it or not? Okay. And then actually in the general case, it is undecidable. Well, yeah. So the trick there is by encode. I mean, one of the ways, now it's been proved in many ways, but one of the ways is by encoding the holding problem for Turing machines as a planning problem, but we don't need to go into that now. I think the main point here is that, well, it is undecidable, and it is undecidable because there's no way of controlling the size of the models. And why not? Well, because the depth of uncertainty can keep growing. So if you know, for instance, about the coordinated attack problems, this is exactly what happens there, that you have these message passings going back and forth. And in principle, the agents know more and more, and they have higher and higher order knowledge, but it just means that you push the uncertainty further down the model, and then it just keeps growing. Anyway, so we looked at we tried to look at, see, can we somehow delimit can we somehow find the border between decidability and undecidability? And of course, well, it depends on what are the parameters you look at. And one of the interesting parameters we found was to look at the modal depth of pre and post conditions. And that's not arbitrary, of course, because the intuition is that the reason that epistemic reasoning is hard is that we have higher order reasoning, right? If we didn't have higher order reasoning, there would not really be a problem if we only have, let's say, 2 agents and 1 proposition, right? So it can only become a problem because I can say, oh, I know that you know that I know that you know that I know, etc., and we can keep on going. So and of course, depth of the model relates to modal depth of the formulas we look at. So that seems natural. Now, then we define some classes of epistemic planning tasks by using these modal depths. So T of M comma N is where we limit the preconditions to modal depth M and the postconditions to modal depth N. So for instance, T00 means that we cannot have epistemic formulas here, and we can also not have epistemic formulas here. Then we have a special case with -1. It means that we don't allow postconditions at all. So that could be a setting where we can only exchange information, but we cannot manipulate green blocks. And here I allow preconditions of depth 2. Here I have 1 and 1. It means that I can have one modal operator in both the pre and post conditions. Okay. So then in a paper from 2020 in the AI journal, we tried to somehow see if we could complete the picture here as, in terms of how does decidability depend on these modal depth, and we almost solved it, but not quite. So I don't think it's maybe also in the interest of time. I don't want to maybe spend too much time on this. Actually, I mainly want to say a few things here. So first of all, the green stuff is where we have decidability. Okay, so and that's actually not so impressive, right? Because it's only when I have propositional preconditions and post conditions or no post conditions at all. So one morale of this picture is that it only takes very little to go into undecidability. That's one thing I wanted to say here. Another thing I wanted to say is that there's an interesting open problem. So if you like difficult open problems, then here's one. So we don't know. We spent some time. We have maybe some intuition, but we still didn't manage to solve this. So if we look at planning, where we allow preconditions of modal depth 1 and no post conditions, it is the planning systems decidable. Planning systems problem, is it decidable or not? That's not known. But other than that, we know. Now, final 2 slides. So because this is more about also the stuff that I'm doing currently. So when you see that, I mean, okay, so what happens in this picture is that when you go up in this lattice, you increase the modal depth of pre and post conditions. So it's like you consider higher and higher order knowledge, right? So, and there is this intuition that if we can bound the depth of reasoning, then we can also kind of bound things. And for many years, I thought about this, that maybe we can define some natural notion of depth-bounded epistemic planning. So let's say we have agents and they can only reason to depth 3, right? For instance, right? So they can nest 3 modal operators, but not 4. And also we know from human reasoning that we rarely reason to more than depth 3, right? So maybe if we just cut off reasoning at some depth, then we get decidable planning. However, it was not completely clear how to deal with that. So this is also very recent work, and that we are currently finalizing and yeah, going to submit very soon. So the idea is based on looking at K by similarity well, by similarity is of course a big thing in modal logic in general, and K by similarity, I don't know if you know it or not, but it's the same as by similarity. You have these forth and back conditions, but you only have them up to a certain depth. Okay. And then K by similarity corresponds to 2 models are K by similar if and only if they agree on all formulas up to modal depth K, right? So if we want to think about reasoning up to a certain modal depth, then it makes sense to look at K by similarity. And then in a recent paper by me and Arnaud Lecon, we have this result that is also like interesting, I think, in general in dynamic epistemic logic, because it talks about preservation of bisimilarity degrees in when you do product updates. It says that if you have k bisimilar states and you have an action where the preconditions are limited by modal depth m, the postconditions are limited by modal depth n, then when you do the product update of these two states with that action, then they are k minus max m comma n bisimilar. Okay, so maybe it's a bit hard to wrap your head around it very fast, right? But the point is, you have two states that are k bisimilar. So intuitively, they agree up to depth k. Then you apply an action. Then they might be less bisimilar than they were before. You apply the same action both places. But it's constrained. We know that we are losing at least the number of bisimilation levels that corresponds to the modal depth used in the pre and post conditions. Okay, maybe that is also a bit strange. So let me try to explain it with a simple example here. So here I have a situation where I have two states that are two bisimilar. It means that if I move only 2 steps away from the designated world, they look the same. They see the same successes, right? And then I take an action that has pre and post conditions of modal depth 1. Okay, like this. What does it mean? It means that we have an action that can look one step ahead of where we apply it. Because if you have a precondition of modal depth 1, it means that, I can look at I cannot look at my neighbors, but I can look at my neighbors, and post conditions similarly. Right, but then that's if it means that, for instance, if I look at this world and that world here, right? So they can see differently labeled worlds, because one can see a Q world and the other one can see a not Q world. Yeah, but that's because I don't have free bisimilarity. But if I look at worlds that are at distance 1 from the designated world, then all they can see at distance 1 is the same. So if I apply an action that can only look at things at distance 1, well, then I'm bound to preserve these properties. So the point is that as long as I know the modal depth of my pre and post conditions, if I apply these actions sufficiently close to, if I apply these actions in worlds, right? I know that they might not preserve the full model, but they preserve it with a reduction in depth that corresponds to these modal depths. Yeah, sorry. I hope it was relatively clear. And then we apply that. And now there's a very technical last slide, so let me not go through that in detail, because I mean, what is important here is just that the intuition of it, which is that we exploit the result from before by saying, but now we can actually look at depth-bounded epistemic reasoning, where we say, instead of looking at the initial state itself, we take the k bisimilation contraction. So we kind of contracted it as much as possible, saying we're only interested in modal equivalence up to depth k. And then we start applying actions. Right, but then we have to be a bit careful, because when we apply actions, we might lose some of these levels of bisimilarity, and depending on the depth of the goal formula, we might be in trouble, or we might be okay. And that's what we exploit. And that's, so as I said, very new work, because it's going to be submitted within the next month. But that's it. Thank you. Now we can have questions.